This lecture on number theory concerns arithmetic progressions and the Chinese remainder theorem. I'm actually going to use the Chinese remainder theorem in several future lessons. I'll try to remind you when I get to it, but this is the first time I'm introducing it in this playlist. An arithmetic progression is an ordered list of numbers such that the difference between two adjacent terms is constant. You've probably seen this even in grade school. I have an example here. Minus 3, 4, 11, 18. You can see that I'm going up 7. The only thing a little bit different is I started here with a negative number. If we let A1 be the initial term of an arithmetic progression and D be the common difference, then the nth term of the sequence is A1 plus n minus 1 times the difference. We also have a formula for the sum of the first n terms in an arithmetic progression, and that's given by this here. So you take the first term and the nth term, multiply by n and divide by 2, and that'll give you the sum. Okay, so let's look at some problems. I'll go through them in this lecture. I have quite a few actually. Let's look at the Chinese remainder theorem. I'll use this a few times in this lecture and other lectures. I have it stated two different ways. One is a little bit more wordy, and then one is more equation oriented. So the conditions are we have n sub 1, n sub 2, all the way up to n sub k integers, which we call moduli, and they're greater than 1. And let n be their product. Then the Chinese remainder theorem asserts that if the n sub I, these integers here, are pairwise co-prime or relatively prime, two different words for the same thing. That just means if you pick any two of them, they don't have any common factors other than 1. If r sub 1 up to r sub k are integers between 0 and n sub I for each I, then there exists one and only one integer x such that x is between 0 and less than n, and the remainder of the Euclidean division of x by n sub I is r sub I for every I. And the r sub I terms need not be unique, so we can pick some of these being the same value if we want. So that's one way of stating it, and it's not all that easy to see. You need to kind of think about it a little bit to get your head around it. But maybe this version helps a little bit. We have the same conditions. We have these n sub 1 up to n sub k moduli, and they're all greater than 1. And n, capital N, is the product of these moduli. And then you have these r sub I that are between 0 and n sub I. And then in that case, this system of equations, modulo n sub 1, n sub 2, all the way up to n sub k, this system here has a unique solution, x, up to modulo capital N. So if there's more than one solution, then they're equal to each other, modulo n. Okay, so that's the theorem. You may need to look at it for a bit to get a feel for it, and hopefully when we look at it in some examples, that'll help reinforce the idea. On this slide, I'm going to describe the algorithm for finding the solution x concerning the Chinese remainder theorem. On the next slide, I'll explain why this works. And then on the slide after that, I'll actually give you an example of doing this calculation. So to find x, the solution to our system of equations, modular equations, we go through these following steps. First, we compute n, so that's pretty obvious, we need that. Then we compute something called n sub I, and that's basically n divided by ni, so it's when you divide by, for example, n1 would just be this product except for n1, and 2 would be this product except for n2, and so on. And then we need to find the modular inverse of n sub I. So we need to solve this equation here for each I, up I equals 1 to k. And it's basically looking at the what number do you need to multiply times n sub I in order to get 1 modulo little n sub I. And we can do that using the extended Euclidean algorithm. And then the example that I give you, we'll just do it by inspection. If n sub I is small, you can normally just go through the possible cases and figure out what the solution is. So we'll do that in our example. And then once you've done this, it's pretty simple. You just take the sum, the r sub I, which is part of the Chinese remainder theorem equations. If you recall, that was each r sub I was between 0 and little n sub I. And then this capital N sub I, which I've described here, over here, step 2, and then these multiplicative inverses, which I've described up here. And that's it. Now, why this works needs a little bit of explanation, and I'll give you that on the next slide. So the one caveat is that x may be large, and if you recall from the statement of the Chinese remainder theorem, you can have multiple solutions, but they're all congruent modulo n. So you just take whatever you get here, and if it's bigger than n, you just take it, whatever it is modulo capital N, and that'll give us our final solution, which will be between 0 and strictly less than n. Okay, so let's look at why this works, why this gives us a solution in the next slide, and then we'll give you an example in the slide after that. On this slide and the next, I want to explain why our solution x that we described a few slides back actually satisfies the system of equations related to the Chinese remainder theorem. The solution for x works because each term in the summation is designed to behave in two very specific ways for, say, equation m, one of these equations here. If it equals r sub m when looked at through its own modulus, n sub m, and it equals 0 when looked at or taken with its any other modulus. So we'll say n sub L, where L doesn't equal m. So let's look at a particular case to make this a little bit clearer. We'll take m equal 1. In other words, we'll look at the first equation here. Consider the term, or any of the terms, where I does not equal 1 in this summation with respect to this first equation. In other words, the term r sub I, n sub I, y sub I not equal to 1. And then if we look at our capital N sub I, we've basically dividing out the n sub I, but since we're assuming I doesn't equal 1 here, we have an n sub 1 term in big N sub I. So n sub I is a multiple of n sub 1. In other words, this product here is congruent to 0 mod n sub 1. This applies to every term in the sum except for the first one, since all n sub I, where I does not equal 1, contains little n sub 1 as a factor, and so they all vanish to 0 when we work modulo n sub 1. Okay, so that takes all of the terms in here except for the first one relative to this equation. We want to look at the first term, and hopefully it'll be r sub 1, because that's what we need in order to satisfy this equation with our definition of x here. And I'll talk about that on the next slide. Okay, so let's continue looking at this first equation here. So we determined that in the summation, all the terms I not equal to 1 modulo n sub 1 or 0, but we didn't look at the first term, which is this here, r1, n1, y1. We want to take that modulo little n sub 1. So now capital N sub 1 doesn't contain little n sub 1 since we factored it out. That's how we define capital N sub 1. So we need to look at the other term. However, we calculated y sub 1 specifically such that it was the inverse of n sub 1 modulo little n sub 1. So this is 1 mod n sub 1. And we substitute that back in, and we evaluate this mod n sub 1. These are 1, as we just said, and then we get r sub 1. So that shows that we've solved the first equation here properly with our definition of x. And it's pretty much the same for the other terms. I just took one to illustrate the point here. But if we're putting this all together, let's verify the solution x for an arbitrary modulus n sub I. We have these terms. First term in the summations, second, then the term, the ith term, and then all the way to the kth term. This is the one that's a little bit different. We take this whole sum modulo n sub I. The term n sub I becomes r sub I times 1, which equals r sub I. It's using this argument that we used up here, but just in general for modulus n sub I. So in other words, the ith equation in this system. All other terms containing n sub I as a factor, and so they all become 0, and thus x is congruent to 0 plus 0 plus 0 up to r sub I for the ith term, then again plus 0, 0, 0, and so on, equals r sub I mod n sub I. So I'm just kind of doing the same argument in general that I did for the first equation here. So this confirms that x satisfies the condition for every single equation in the system of equations. Well, let's look at a problem. Find x such that x satisfies these three modular equations, and you would use the procedure, the algorithm that we talked about in the last several slides concerning the Chinese remainder theorem. If you want to give it a try, hit the pause on the video now, because I'm going to show you the solution on this same slide. Okay, so let's proceed with the solution. So using our algorithm, R1, R2, R3 are just these values here, 2, 3, and 2. And it's allowed to repeat them. And you notice 2, 3, and 2 are all between 0 and 7, 0 and 5, 0 and 3. So we meet that criteria. Then the ends, of course, M1, N2, N3 are 3, 5, and 7. Then we calculate capital N, that's just 3 times 5 times 7, 105. Then N sub 1 is N divided by N1, you get 35. N sub 2 is N divided by little n sub 2, you get 21. And big N sub 3 is N divided by little n sub 3, so that's 15. Then we need to find the modular inverses for y1, y2, and y3. So the first one here is n1, which I plugged in already, times y1 equals 1. So we want to find y1 that satisfies this. The first thing we can do is simplify 35 mod 3. It's just 2 mod 3, and then put that back into this equation. We get 2 times y1 congruent to 1 mod 3. So what we can only pick between 0, 1, and 2. And you can see pretty quickly if you pick 2 for y1, you get 4, and that's congruent to 1 mod 3, so y1 is 2. And the other two are even simpler. 21, taking the n2 times y sub 2. When is this, for what value of y2 is this congruent to 1? So again, we reduced 21 mod 5 first, and we see it's just 1, and we plug that back in for 21. So it's even more obvious here. We just need to have y sub 2 equal 1 to satisfy this. And the third one is just as easy. You want to solve 15, y sub 3 congruent to 1. 15 is congruent to 1 mod 7, right? 2 times 7 is 14, and then you have 1 left over for 15. And so you have the equation 1 times y sub 3 congruent to 1, and again y sub 3 is 1. So now we have all our values that we need for the formula for x. So here's the formula for x. Since we only have 3 equations, we have 3 terms, and we just take our r1, r2, r3, 2, 3, and 2, the m1 and 2 and 3, plug those in, and then y1, y2, y3. We just multiply these out. The first one is what? 70 times 2 is 140. 3 times 21 is 63. 30. X is 233. But we want to find it mod 105. And it's pretty easy to do. We take 233 mod 105 twice. 105 is 210. And that leaves a remainder of 23. So that's our solution. You may want to go back and put 23 in here and just check to see that it satisfies all 3 of these equations. We can just do one here. Let's see. We put in 23 for this one here. We get 23 is congruent to 3 mod 5. And if you subtract the 3 from the 23, you get 20. And of course, 20 is congruent to 0 mod 5. So that checks out. So you may want to check the other two, but they both work out. Okay, so we spent a lot of time on this. It comes up, meaning the Chinese remainder theorem. It comes up in some other problems, so I thought I would take some time to explain it. It's not all that easy to absorb unless you kind of look at it in terms of the details of the algorithm and then doing a little example like we did here. Let's look at another problem. Construct a sequence of 5 composite integers in an arithmetic progression that are pairwise relatively prime. So composite means not prime. It means the number is divisible by a number other than itself and 1. So for example, 10 is composite. It's divisible by 2 and 5. In addition to 1 and 10. So we want to find 5 composite integers in a progression, an arithmetic progression, so they're separated by the same distance, and they're relatively prime, so they don't share, even though they're composite, they're relatively prime or co-prime in the sense that they don't share any divisors. Okay, so this is pretty hard. I'll give you a hint. Or at least one way of solving it is to use the Chinese remainder theorem, and I'll go through it. It's going to take several slides to actually explain it, but if you want to try it, you may want to pause here. Otherwise, I'll come back and I'll show you the solution. This problem can be solved using the Chinese remainder theorem. The challenge is to satisfy the 3 constraints that we were given in the statement of the problem. So to start out, we'll label the sequence. We don't know what it is yet, of course, but we'll label it A1 to A5. And then we'll call the difference between each 2 terms in sequences to be D. And then these are the 3 conditions. I'm just writing them out a little more formally. So we need to have an arithmetic progression. In other words, this relationship here. Each of the terms need to be composite. In other words, they need to have at least 2 prime factors. And then any 2 of these terms not even in succession, right? It could be A1 and A4. They have to have a GCD of 1. So here's the strategy. And you may want to take this as a hint and then pause the video here and try to solve the problem. To ensure the numbers are composite, we will force each term A sub k to be a multiple of a distinct product of primes. We must ensure the numbers are pairwise relatively prime while effectively managing the common difference. And then we have two facts here. The greatest common divisor of any two terms in an arithmetic progression, so in other words, this GCD here, A sub I, A sub j, must divide the difference of their indices times d. So this GCD must divide j minus I times d. And then we have another property here. The GCD of A sub I, A sub j is equal to the GCD of A sub I with j minus I times d. I'll prove these two things on the next slide. Since the maximum separation between indices is 4, right, that would be between A1 and A5. We're only asked to look for a progression with 5 terms in it. Any common factor must divide 4d. That's from this statement here. If we eliminate all small prime factors 2 and 3 from our terms and correctly choose d, we can force the GCD to be 1 between any two of these terms. These are the two statements from the previous slide that I said we need to prove. First one, we want to show this GCD divides j minus I times d. So we'll let G equal the GCD, and by definition, G divides both A sub I and A sub j. The fundamental property of divisibility states that if an integer divides two numbers, it must also divide their difference. In fact, it also divides any linear combination, but we just need their difference. So G divides A sub j minus A sub I. Substitute the arithmetic progression formula for the difference between A sub j minus A sub I. So we have that here. Then A sub j is this term here. You just take the smaller term and then add to it the difference in the indices times d. So this is A sub j, and then you carry over the minus A sub I, and this A sub I and this A sub I cancel. And you get the difference equals j minus id, but we establish here that g divides the difference, and since the difference equals j minus id, that means g, the GCD, this thing here, divides j minus I times d. So that's what we wanted to prove here. Then the second statement, which I copied over here, we want to make use of the Euclidean algorithm. So for any u, v, and k, we have u, the GCD of u and v is the same as the GCD of u, v minus ku. And we'll take u to be ai and v to be a sub j, and k will just be 1 in this case here. So that's what I have here. I have, you notice the a sub j minus 1 times a sub I, just using this part of the formula. Then we bring down the a sub I, and for a sub j, as we did here, we use the formula for the progression. So that's here, and then we have minus the 1 times AR. I just wrote it down as a sub I. Then the a sub i's cancel, and you get our desired result. Okay, now for the construction of our solution. We start with choosing D, our difference between the terms would be 30. And the reason we do that is the 30 is 2 times 3 times 5, and it has a divisor of 6, which means that a sub k is congruent to a sub 1 mod 6 for all k, which would be 2, 3, 4, and 5. If we pick the first term a sub 1 such that a sub 1, the GCD of a sub 1 was 6 equals 1, then the GCD of a sub I with respect to 6, we just plug this in for the definition of a sub I. We get this here. Then we can factor a 6 out. And then we use the Euclidean algorithm to say that this equals this here. And so we see that the GCD of a sub 1 I, was 6 is 1. This prevents the numbers from sharing factors 2 and 3 because of this GCD being 1, which are the only prime factors that could arise from the indices 1, 2, 3, and 4. Okay, then we proceed. We wanted to select distinct primes. We're going to need 10 of them, one for each of our elements in the progression, all greater than 5. This ensures that the prime factors we introduce do not interfere with our coprimality strategy, since they are coprime to the difference equaling 30 and to the index differences. They referring to these 10 distinct primes, which I've listed here. Okay, so clearly they're prime numbers. They're coprime, relatively prime with 30. None of these numbers divide 30. And then we proceed to assigning composite factors. Now these are the n sub j's in the Chinese remainder theorem. So we're going to pair these primes to create 5 distinct composite moduli. Each term a sub k will be constructed to be a multiple of its assigned n sub k. So this will become clearer on the next slide, but we're setting up the Chinese remainder theorem. Then we're going to solve that, and that'll give us our x. So n sub 1 is just the product of the first two, n sub 2 is the product of the second two, and so on. Okay, so this is just setting up the equations in the Chinese remainder theorem. We'll see what that looks like on the next slide. Okay, as I said, we're going to construct the congruences for the Chinese remainder theorem in this slide. We need to find a starting number x. This will be our a sub 1, such that the entire sequence fits the moduli defined on the previous slide, the different n sub i's. And then our sequence will be x, x plus 30, x plus 60, and so on. So we'll have an arithmetic progression where the difference is 30. Then we need to have any two of these being relatively prime, and we'll see that they'll be the case. And then we also need to have that each one of these numbers is composite. X, x plus 30, and so on are composite. Those are the 3 requirements. Okay, so we're going to put down our system here. First one is x. We want x to be congruent to 1 mod 30. This ensures x is not divisible by 2, 3, or 5. Since d equals 30, all subsequent terms will also be congruent to 1 mod 30, ensuring no term is divisible by 2, 3, or 5. Then we have these 5 conditions. X is congruent to 0 mod 77. Remember, 77 was the moduli, the first one we defined, n sub 1. So this ensures that A1, which is our x, remember we have that here. So our A1 is a multiple of 77. And of course it's composite because 77 is a product of 2 primes. Then we have x plus 30. is congruent to 0 mod 221. This was our n sub 2, but we want to take the 30 to the other side. We want to get this into a form we can apply the Chinese remainder theorem to. So we move the 30 here, it'd be minus 30, and then we add 221 to it, we get 191. So A2 is a multiple of 221, which is, again, not prime, it's a composite. And then we just proceed, we have x plus 60, we bring the 60 over here, so minus 60, we add 437 to it, and we get 377. And so this ensures A3 is a multiple of 437, which is a product of two primes. We do the same thing here, same thing here. And then the solution, we know the solution exists since the moduli 30, 77, 221, so on, are pairwise relatively prime. Right, that was from our painstaking construction. And these latter five are all products of two prime numbers, and we made sure they didn't share anything with these factors of 30, which were 2, 3, and 5. And then the Chinese remainder theorem guarantees that a unique solution X exists modulo their product N, product of all these together. The smallest positive integer X satisfying the system will generate the desired sequence, while X will be large number, likely 10 to the 10th power. The existence and properties of the sequence are mathematically guaranteed by this construction. Well, we're actually going to find it, so we don't need to rely on just the guarantee that there's a solution existing. And this is the final result. The value of X serves as the first term, which I'll show you a program to actually extract that. But the first term is A1, and it's this huge number. And it's divisible by 77. So it's composite. And then after that, it's easy. Once we've computed this, then you're just adding 30. You notice this is 30. This is divisible by 221. You can check it if you don't believe me. Then we add 30 again. This is divisible by the 437, which is the product of two primes, such as this was. So it's composite. And this is the next one. We just added 30 again and 30 again. It's divisible by the last two moduli, n sub 5, n sub 4, and n sub 5. These are products of primes, so this number here is composite, and this number here is composite. Okay, so let me show you how I got this in the remaining few slides. So I used Python to do this. So this is a Python program. It's on this slide and on the next slide. I imported Chinese remainder theorem. Believe it or not, there's a package for that. I imported math and GCD. And it's pretty easy, actually. You just give it the moduli. These are the numbers we constructed. And then these were the remainders. You remember we derived those a couple of slides back. And that's all you need to give it. You just call the Chinese remainder theorem, and you give it the moduli and the remainders. You tell it the well. We also input the common difference here, and this gives us back X, which is our A1, and then we're just going through a loop here to add 30 to the solution we get here. So that's done here, and then we print it out. And there's one more bit to the program here. I'll show you that on the next slide. This is the main part of it. You really just need this here. And this second part of the program is just checking the conditions. So the first part is checking that the results, the A1, A sub 2, the numbers in our arithmetic progression, that they're in fact composite. And so we just divide here and make sure that there's no remainder. And then we print that out. If that checks out okay. You notice here we're going term by term. These are the A sub i's. And this is the part that checks to make sure that there's no remainder. And then this second part here is to make sure that each of the pair of the solutions that we found, A1, A2, A3, and so forth, that any two of those are relatively prime, that their GCD is 1. So that's what we're checking in here. And then it prints out the result. And on the next slide, I'll show you the printout of running this. Okay, so here's the result. This is the bit that comes out of the first slide that had the first part of the program. So this is our A sub 1, and then this is just the entire arithmetic progression. It takes your X and makes that A sub 1, and then it adds 30, adds 30, 30, and 30 again. And that's really what we wanted to get at. We kind of knew that the numbers were composite because we constructed them to be that way, and we also knew they were relatively prime, but this is just showing the checks here. So for the A1, it checked to see that 77 divided into this, and so we knew it was composite. Same thing for the second one, third one, fourth one, fifth one. And then here we just checked taking 2 at a time out of the 5 elements in our arithmetic progression. We checked to make sure they all had GCD 1, which it did, and then we just printed out that they're all co-prime or relatively prime, and we said that was true. Okay, so that's the last item from this particular lecture. I have a second lecture on arithmetic progressions, which I'll follow after this, and I'll also try to give you a link to where the program is. I don't think I can post it on Facebook, but I might be able to put the program on GitHub and then give you a link to get there, and so you don't need to type it in if you want to test it yourself.